This is part 2 of a video about exponential and logarithmic equations and inequalities. This is AP Pre-Calculus topic 2.13. If you did not see part 1, you can either click the link that appears in the upper right hand corner or find the link in the description. If you appreciate this content, please give it a like. Number 12, let h of x equal the natural log of x squared plus 5 and let k of x equal the natural log of 7x minus 7. What are all the values of x for which h of x is greater than k of x? In order to ultimately make a sign chart. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there. We need 0 on one side. So let's subtract k of x from both sides of this inequality, which will give us h of x minus k of x is greater than 0. Also, it will be more convenient if we call the left side of the inequality by a single name. So let's let f of x equal h of x minus k of x. As before, we begin by finding where f of x equals 0. So that means finding where h of x minus k of x is equal to 0. But adding k of x to both sides, again, we get h of x is equal to k of x. So we're going to just set these two log expressions equal to each other. F of x will equal 0 when the natural log of x squared plus 5 is equal to the natural log of 7x minus 7. When a log is equal to a log, the argument on the inside is equal to the argument on the inside. So x squared plus 5 is equal to 7x minus 7. We can solve this equation by getting 0 on one side. So I'm bringing down the x squared, and I am subtracting 7x from both sides. So x squared minus 7x. Let's add 7 to both sides, and we get plus 12 is equal to 0. I am hoping that this trinomial is factorable. X squared will factor as x times x. 12 will factor as 2 times 6, or 3 times 4, or 1 times 12. Looking at the middle, I'm going to go with 3 times 4. To make the negative 7x in the middle, we need a negative 3x inner and a negative 4x outer. Also, negative 3 times negative 4 gives us the positive 12 that we also do need. By the zero product property, we know that x will equal 3 or x will equal 4. These are the first two critical values that will go on the sign chart later. In addition, we need to find where f of x is undefined. You cannot take the natural log of 0. So f of x will definitely be undefined when x squared plus 5 is equal to 0, or when 7x minus 7 is equal to 0. This first equation has no real solutions. X squared is always going to be greater than or equal to 0. If you take the number 5 and then add to it something that is greater than or equal to 0, there's no way that these will cancel out and equal 0. Another way to think about it is if you try to solve this by subtracting 5 from both sides, then we get x squared is equal to negative 5. Again, right there, you cannot square something and get a negative number, so no real solutions. Or if you kept going and you took the square root of both sides, then you would get x is equal to plus or minus the square root of negative 5. This is going to be imaginary. We will get another critical value from the other equation. Adding 7 to both sides, we get 7x is equal to 7. And dividing both sides by 7, we get x is equal to 1. Next, we can make a sign chart with these three critical values in order across the top. Remember that f of x is equal to h of x minus k of x, natural log of x squared plus 5 minus the natural log of 7x minus 7. We need to determine whether f of x is positive, negative, or undefined in each one of these intervals. So let's use a test value in each interval. Let's begin by evaluating f at 0 for the first interval. Plugging in 0 for these x's gives us the natural log of 5 minus the natural log of negative 7. But you cannot take the natural log of a negative number, so f at 0 is undefined. So f of x will be undefined in the first interval. For the next interval, let's use a test value of 2. So let's evaluate f at 2. Plugging in 2 for these x's gives us the natural log of 4 plus 5 minus the natural log of 14 minus 7. This equals the natural log of 9 minus the natural log of 7. Since the natural log of 9 is bigger than the natural log of 7, this difference is positive. So f of x will be positive in this interval. For the next interval, let's use, well, I guess we have to use like 3.5 as the test value. I don't like that very much. Okay, this is going to be annoying, but 3.5 is the same as 7 over 2. So to keep it exact, that's what I'm going to use. 7 over 2 squared is 49 over 4. So we have the natural log of 49 over 4 plus 5. 7 times 7 over 2. 7 times 7 is 49, so we have 49 over 2 minus 7. To make like denominators, we can turn 5 into 20 over 4, and we can turn 7 into 14 over 2. Combining the fractions, we have the natural log of 69 over 4 minus the natural log of 35 over 2. For easy comparison, let's make these into like denominators as well. So multiplying the 35 over 2 by 2 over 2, we get the natural log of 69 over 4 minus the natural log of 70 over 4. This second expression is bigger, so the value of this expression will be negative, which is all that matters. So f of x is negative in this interval. In the last interval, let's use a test value of 5. Plugging 5 in for these x's gives us the natural log of 25 plus 5 minus the natural log of 35 minus 7. This equals the natural log of 30 minus the natural log of 28. Since the first expression is greater than the second, the difference is positive. So f of x is positive in this last interval. Remember, we were looking for where h of x is greater than k of x, which means we were looking for where h of x minus k of x is greater than 0, which means that we are looking for where f of x is greater than 0. So the solutions to the inequality will be in these intervals where f of x is positive. The endpoints of these intervals are not to be included because we are looking for where f of x is greater than 0, not greater than or equal to 0. That's why I am marking them with open circles, and when I write the solution set in interval notation, I should use parentheses, not brackets. So this will be the interval from 1 to 3, union the interval from 4 to infinity. Number 13, let p of x equal 12 plus 5 times 3 to the 4x plus 1 power. What are all the values of x for which p of x is greater than or equal to 57? We do not need to make a sign chart to solve an exponential inequality. We can just set up the inequality and solve for x. Subtracting 12 from both sides, we get 5 times 3 to the 4x plus 1 power is greater than or equal to 45. Dividing both sides by 5 leaves us with 3 to the 4x plus 1 power is greater than or equal to 9. I'm sliding the 9 over to make room for my next move, because we can make this base 3 go away by taking the log base 3 of both sides of the inequality. On the left side, the log base 3 and the base 3 cancel each other out, leaving behind 4x plus 1. So we have 4x plus 1 is greater than or equal to. And then the log base 3 of 9 has a value of 2, because 3 to the second power is 9. Subtracting 1 from both sides gives us 4x is greater than or equal to 1. And dividing both sides by 4 gives us x is greater than or equal to 1/4. And that's the answer. Number 14, back to logarithms. Let f of x equal this whole expression. What are all values of x for which f of x is greater than 3? Ultimately, we will use a sign chart to solve this inequality. So let's get 0 on one side by subtracting 3 from both sides. So f of x minus 3 is greater than 0. First, we need to find where f of x minus 3 is equal to 0. So we need to solve this equation right here. On the next step, I'm going to do two things. I'm going to move the 3 back over to the right-hand side of the equation for now. So we will have equals 3. And on the left side, we've learned that we can combine the difference of two logs into the single log of a quotient. So I'm going to set up this divided by this. That brings us to here. We can make the log base 2 go away by dropping a base 2 on both sides of the equation. So on the left side, the base 2 and the log base 2 will cancel each other out, and we will be left with this fraction. On the right side, 2 to the third power is 8. That brings us to here. On the next step, I will eliminate this fraction by multiplying both sides of the equation by the denominator. So now we have this. Let's distribute the 8. Now we have this. Subtracting 16x from both sides gives us x squared minus 6x. Then adding 8 to both sides gives us plus 32 is equal to 0. Hopefully this is factorable. X squared will factor as x times x. Among other things, 32 is 4 times 8. This will not allow me to get a middle of -6. So it is at this point that I realize that this trinomial is not actually factorable, and we need to use the quadratic formula. X will equal the opposite of b, so positive 6, plus or minus b squared, which is 36, minus 4 times a times c, which is 32. This equation will have no real solutions, because 36 minus 4 times 32 will obviously be a negative number. 4 times 32, that's like 128 or something, so we're subtracting a really big number. This is going to be negative under the radical. That's imaginary, so no real solutions here. That means the only critical values on the sign chart will come from where f of x minus 3 is undefined. You cannot take the log of 0, so f of x minus 3 will definitely be undefined when this trinomial is equal to 0 or when 2x minus 1 is equal to 0. Let's start with setting the trinomial equal to 0. Hopefully this is factorable. X squared will factor as x times x. Among other things, 24 is 4 times 6. Inner plus outer must equal middle. So with a 4x inner and a 6x outer, we can get a positive 10x if we just leave both of these as a positive. Also, positive 4 times positive 6 gives us the positive 24 that we also need. The zero product property tells us that x equals negative 4 or x equals negative 6. Now let's set 2x minus 1 equal to 0. So this will give us 2x is equal to 1 and x is equal to 1/2. Let's make a sign chart using these three critical values. We need to determine whether f of x minus 3 is positive, negative, or undefined in each interval. This big expression is f of x minus 3. We need to use a test value in each interval to see whether f of x minus 3 is positive, negative, or undefined. In the first interval, let's use negative 7. So if we plug in negative 7, for example, right here, 2 times negative 7 is negative 14. Minus 1 is negative 15. You cannot take the log of a negative number, so f at negative 7 minus 3 is undefined. For the next interval, let's use negative 5. But we run into the exact same issue. If you plug in negative 5 right here, 2 times negative 5 is negative 10, minus 1, that's negative 11, also undefined. In the next interval, we can use 0. However, we still have a problem. If we plug in 0 right here, we are left with negative 1. You cannot take the log of negative 1, so this will still be undefined. For the last interval, let's use a test value of 1. If we plug in 1 for these x's, we get the log base 2 of 1 plus 10 plus 24 minus the log base 2 of 2 minus 1, and then minus 3. This simplifies down to the log base 2 of 35 minus the log base 2 of 1, minus 3. The log base 2 of 1 is 0 because 2 to the 0 power is 1. So this term is gone. We just need to figure out whether the log base 2 of 35 is bigger or smaller than 3. One way to do that is to turn 3 into a log expression with a matching base. I can do that by multiplying 3 by the log base 2 of 2. The log base 2 of 2 is 1, so I'm multiplying by 1. This will not change anything. Now we can use the properties of logarithms to move this 3 to the exponent. So this will become log base 2 of 2 to the third power. This will become an 8 on the next step. Now we can see that the first log is bigger than the second log. So this difference is positive. Back to the sign chart. F of x minus 3 is positive in this last interval, and we are looking for where f of x minus 3 is greater than 0. So the solutions will be in this final interval. The final answer can either be written in interval notation as the interval from 1/2 to infinity, or as an inequality, x is greater than 1/2. Number 15, f of x is equal to e to the x power to the third power divided by e squared. Solve f of x equals e to the fifth power for values of x in the domain of f. So we need to set f of x equal to e to the fifth power. When you raise a power to a power, you multiply. So I went ahead and wrote e to the 3x power. We can eliminate the fraction by multiplying both sides by e squared. On the left side, we just have e to the 3x power. On the right-hand side, when you multiply with like bases, you add these exponents. So we get e to the 7th power. Now, on both sides of the equation, we have base e. Therefore, the exponents must also be equal. So we can just set 3x equal to 7. Dividing both sides by 3, we get x is equal to 7/3. And that's the answer. For number 16, we are given this expression for k of x, and we need to solve k of x equals e to the 1/2 power. So we will simply set k of x equal to e to the 1/2 power and solve. Again, when you raise a power to a power, you multiply, so I've written 4x. We can get rid of the fraction by multiplying both sides by the denominator, e to the 1/3 power. On the left side, we will just have e to the 4x power. On the right-hand side, when you multiply with like bases, you add the exponents. So we need to add 1/2 and 1/3. We need to have like denominators in order to do this. So let's multiply 1/2 by 3/3, and let's multiply 1/3 by 2/2. So this will make 3/6 plus 2/6, which is 5/6. Since the bases are equal, the exponents must be equal. So 4x equals 5/6. Dividing both sides by 4, we will have x is equal to 5/24. That's because when you divide a fraction by 4, you just multiply by 4 into the denominator. So this is the final answer. Number 17, j of x is equal to this expression, and we need to solve j of x equals 2e. Setting j of x equal to 2e gives us this equation. I see some like terms happening here, so let's add 3e to both sides of the equation. That will give us e to the 2x is equal to 5e. To be able to solve this, I really need to have just e in one place in this equation. I can accomplish that by dividing both sides of the equation by e, like this. So on the right-hand side, the e's will cancel each other out. But on the left-hand side, think of this as e to the 1 power. When you divide with like bases, you subtract the exponents. So on the left side, we will get e to the 2x minus 1 power. I'm subtracting these two exponents, and this will equal 5. I can now get rid of the base e by taking the natural log of both sides of the equation. On the left-hand side, the natural log and the base e will cancel each other out, leaving behind the 2x minus 1. On the right-hand side, we are stuck with natural log 5. So now we just have to do some algebra. Let's add 1 to both sides, which will give us 2x is equal to the natural log of 5 plus 1. And then if we divide both sides by 2, we get x is equal to the natural log of 5 plus 1 all over 2. And that's the final answer. Number 18, m of x equals this expression, and we need to solve m of x equals e. So let's set this expression equal to e. This e is like 1e. Think of it that way as you add 5e to both sides of the equation. So on the left side, I will still have 3 times e to the 4x, but on the right-hand side, I will have 6e. Let's go ahead and divide both sides by 3. So then we will have e to the 4x is equal to 2e. I would like to get these e's together. I can accomplish that by dividing both sides of the equation by e. So on the right side, these e's will cancel each other out, but on the left side, I'm going to think of this as e to the 1 power. And you know that when you divide with like bases, you subtract the exponents. So this will be e to the 4x minus 1 is equal to 2. We can make this base e go away by taking the natural log of both sides of the equation. So if I do the natural log on the left and the natural log on the right, on the left side, the natural log and the e will cancel each other out. And we are left with 4x minus 1 is equal to the natural log of 2. Adding 1 to both sides, we get 4x is equal to the natural log of 2 plus 1. And dividing both sides by 4, we get x is equal to the natural log of 2 plus 1 all over 4. And that's the final answer.